All right, let's talk about something that sounds incredibly complicated, Bayesian networks. But I'm going to let you in on a little secret. It's actually not that bad. In fact, by the end of this, you'll see it's really just about using a map and a rule book to tell a story. So let's dive right in.
So here it is. This is our map. Now, I know it looks a little abstract, but just think of it as a story of cause and effect. It shows us how these different events, we're just calling them U, V, W, and Z, influence each other. The real magic is in the arrows. They show us the path of that influence, a bit like a flowchart of possibilities.
And that map brings us to the big puzzle we're going to solve together today. If all these dominoes fall in a very specific way, what are the actual, concrete chances of that happening? Let's figure it out.
Okay, so to solve this puzzle, we have to start with the basics, and that means learning how to read our map. Let's break down what these circles and arrows are really telling us. Honestly, it's pretty straightforward. The circles, those are just our events, and the arrows, they show who influences who. So when you see an arrow pointing from U to V, all that means is that what happens with V, well, it depends on what happened with U. Simple as that.
And this is a really key idea. Take a look at U. See how there are no arrows pointing into it? That means it's our independent variable. It's the start of the whole chain reaction. But V and W, on the other hand, they do have an arrow coming from U. That makes them dependent. Their fate is tied to whatever U decides to do.
And then we get to Z. It's kind of the grand finale of our map. You can see it has two arrows pointing its way, one from V and one from W. That makes Z the most dependent event here, because its outcome hinges on two separate things coming together.
Okay, so we know how to read the map and see the connections, but that's just the layout. What about the actual rules of the road? For that, we need to open up our rule book, which is really just a set of cables with all the specific probabilities.
Let's start with the easiest one, the rule for U. Because U is independent, its rulebook is super simple. It just says there's a 60% chance that U happens and a 40% chance it doesn't. That's it.
Now for V. Since V's outcome depends on U, its rulebook is a little more detailed. This is what we call a conditional probability table. It's just a fancy way of saying it shows us the odds for V depending on what U did. So you can see if U is 1, there's a huge 80% chance V will be 1 too. The table just gives us the numbers for the dependency we saw on the map.
And here's the big one, the rule book for Z. I know, it looks like a lot, but because Z depends on both V and W, its table just needs a line for every single possible combo of its parents. The logic is exactly the same, it's just covering all its bases.
Okay, we have our map, we have our rule book, we have officially got all the tools we need. So now, let's put everything together and finally answer that big question we started with.
Just to be perfectly clear, this is our goal. We want to know the exact odds that every single one of these events ends up as a 1.
The secret to cracking this is something called the chain rule. Now, that sounds way more intense than it is. All it really means is that we're going to find the probability for each event, one by one, based on its parents, and then just multiply them all together.
And here is what that looks like in math speak. But don't let the notation freak you out. It's just a recipe. It's telling us to find the probability of Z given its parents V and W, then multiply that by the probability of V given its parent U, and so on, all the way down the chain. We're just following the arrows.
All right, here we go. This is the fun part. We're going to take that formula piece by piece and just pull the numbers we need straight from the rulebook tables we just looked at.
First up, we need to know the chance of Z being 1, assuming that both V and W are also 1.
So we just go to our rulebook for Z. We find the row where V is 1 and W is 1. Then we slide over to the Z equals 1 column and boom, there's our number.
Our first number is 0.9. Awesome, 1 down, 3 more to go. Next on the list, what's the probability of V being 1 given that its parent U is also 1?
Back to the rulebook for V we go. We find the row for U equals 1, look at the column for V equals 1, and we've got our second piece of the puzzle. It's 0.8.
You know the drill by now. Same thing for W. What's the chance of W being 1 given that U is 1?
We'll check the W table. We go to the U equals 1 row, then look across to the W equals 1 column, and our value is 0.1.
And finally, the easiest one of all. We just need the basic probability that our independent event, U, is equal to 1.
We go to that first simple table for U, and the answer is right there waiting for us, 0.6. And just like that, we have all 4 pieces we need.
We've navigated the map, we've consulted the rulebook, we've gathered all of our numbers. Now it is time to put it all together and get our final answer.
So remember the chain rule? It just told us to multiply all those probabilities we found. So let's do it. We've got 0.9 times 0.8 times 0.1 times 0.6.
And when we crunch those numbers, we get our final answer, 0.0432.
So what does that mean? It means there is exactly a 4.32% chance of U, V, W, and Z all landing on 1 together. We've solved the puzzle.
But here's the thing. This isn't just a neat math trick. This exact logic, using a map of dependencies, is a powerhouse in the real world. It's used in medicine to help diagnose diseases by connecting symptoms to conditions. It's what helps your email figure out what's spam. And it's used to model unbelievably complex systems, like the stock market or weather patterns.
And that kind of leaves us with one last big question. Now that you know the basics of how these maps work, what could you use one for? What complex system out there could you start to predict? The possibilities are pretty much endless. Thanks for digging into this with me.